Bueno, buenas tardes o buenos días. Thanks to the organizers of this international meeting on Lorentzian geometry. It's good to be here with you online. I will speak about null hypersurfaces, and some parts of this talk is a joint work with Matias Navarro and Didier Solis from the University of Yucatan in Mexico. So, what is the plan of the talk? I will speak about null submanifolds, so I will give some background on this area. In particular, I will talk about the screen distribution, which is a technique that is very useful to study this kind of objects. And I will give some results in the area. The first one is a well-known result about total umbilical null hypersurfaces, which was obtained by many authors. Then I will speak about some work on screen parallel shape operators for these submanifolds. And in the last part of my talk, I will speak about the isometric immersion problem for this kind of null submanifolds. Okay, so some background, although I think that many people here know this definition, so I will speak about them very quickly. If we give a vector space B, we say that a scalar product is a symmetric bilinear form, which is not degenerate. This means that if there is some vector field U, which is orthogonal to every other vector fields, then U is equal to 0. And the standard example is the scalar product on Rn of index k, which is given in this form with k negative signs and minus k positive signs. So this is a scalar product, and a semi-Riemannian manifold is a differentiable manifold with a non-degenerate semi-Riemannian metric, which means that for every point in this manifold, we give a scalar product in the sense of above, which varies smoothly, and in particular, it means that it implies that it has constant index. And if we have this environment, a differentiable submanifold M is semi-Riemannian if the restriction of the scalar product of M bar to the tangent space of M at each point is once again a non-degenerate scalar product. So the standard examples of these objects are the Lorentz-Minkowski space, which has this so-called Lorentz metric, the de Sitter space, which can be seen as an hyperquadric in the Lorentzian Minkowski space, and also the anti-de Sitter space, or the pseudo hyperbolic space, which can be seen also as a hyperquadric in some Lorentz-Minkowski space. Okay. We know that all of our knowledge of differential geometry works fine in the semi-Riemannian case. We have the Levi-Civita connection, the curvature tensor, and so many other things. And in particular, these examples here are those simply connected spaces with constant sectional curvature. What happens for the degenerate case? The standard example is the light cone in Lorentz-Minkowski space, which of course is, we all know that it can be seen as a cone, okay? And as this example suggests, this kind of degenerate cases are motivated somehow by physics. For example, also some kind of horizons are examples of null manifolds or degenerate manifolds. So it is important to study these kind of things, and we study them from the geometric point of view. So let's state some notation. M bar will be a Lorentzian manifold. That means that our metric G bar has constant index 1. M will be hypersurfaces, and the restriction G of the metric G bar to each tangent space will be degenerate. And we say in this context that M is a null hypersurface. It can be seen that this is equivalent to the existence of a vector field, which we call here Xi, everywhere different from 0, which is both tangent and normal to M. This vector field generates some bundle over M called the radical bundle. So let's do some geometry. Just remember that in the case of a Riemannian manifold M bar and the hypersurface M, we have the Levi-Civita connection, nabla bar, and this connection applied to vector fields can be decomposed into two components because we have this direct sum decomposition. Of course, the tangent part of this connection gives us the Levi-Civita connection of M, and the normal part gives rise to the second fundamental form. In the degenerate case, we cannot do this procedure because we have, as said, the intersection of Tm and Tm perp is not 0. So we don't have this decomposition. So we have to do some additional work, which can be done as follows. Since at every point of the hypersurface we have the direction given by Xi, and essentially it is very easy to understand the behavior in this direction. We take all directions complementary to this direction, to the Xi direction, and use this this cut to study the geometry of M. So we will state our definitions in terms of some distributions in the following way. We say that screen distribution on M is a distribution S of Tm complementary to the radical or to Tm perp in Tm bar. Okay. So we will study this kind of objects, M, the metric G, and the screen distribution. Okay, and it is known that if we fix our distribution S of Tm, then we have a vector field called the transversal bundle, rank 1, such that it is orthogonal to every direction in the screen, and also is spanned by some null vector field n. And we have this kind of, let's say, orthogonality or normalization condition, okay? We will work in a neighborhood where all these sections xi and n exist. Then we have this nice decomposition, the tangent bundle of M bar is decomposed in direct sum given by the tangent bundle of M plus the transversal bundle, and also the tangent bundle of M is decomposed by the sum, the screen distribution, and the radical. Okay, so we have this decomposition for the whole tangent bundle of our ambient space. And just to fix notation, we call P the projection of this thing, this collection of sections of the tangent bundle, means the vector fields, over the collection of sections of the screen distribution. Okay, just to fix notation. So we can do now what was done in the remaining case. We have nabla bar, the Levi-Civita connection, and for each xy vector fields on M, we have these decompositions, which look somewhat like the usual decompositions, but now we have this part, for example, in the direction of n, and also we have these decompositions on the tangent bundle of M. Okay, so this part, for example, is tangent to the screen distribution, and this part is the direction of xi in the radical bundle. Okay, so we have a lot of connections. We have 4 connections, 4 linear connections on each of these objects: the tangent bundle, the transversal bundle, the screen distribution, and the radical. And also we have 2 second fundamental forms, which are called H and H star. Also we have 2 local second fundamental forms and 2 shape operators. Okay, just for this notation here, we just define this one form tau just by this formula here. Okay. So as we have all these connections, we also have some curvature tensors, and we have some Gauss equations in these forms. Okay, we just put these Gauss equations in the case where the ambient space have constant curvature, C bar. Okay, which appears, for example, here. Okay, and okay. So as we have two shape operators, it is somewhat natural to establish some relations between them, just study the null submanifolds. So Atendogbe and Dugal define the following concept. A null hypersurface is screen conformal if and only if the shape operators are related in this way. And this concept is useful for studying the geometry of these objects. For example, we have this kind of result. Let us recall that a null hypersurface is totally umbilical if and only if the second fundamental form is a multiple of the metric in this way. And in the case where the constant lambda is equal to 0, then we say that M is totally geodesic. So if the null hypersurface is screen conformal, then the screen distribution is integrable, and M is totally geodesic or totally umbilical if and only if each leaf of the screen distribution is a non-degenerate, totally geodesic or totally umbilical submanifold of codimension 2. So this kind of result relates the geometry of the null hypersurface to the geometry of these leaves. Okay. Let us see what happens in this kind of useful examples. Let us recall that M bar is a generalized Robertson-Walker space if it is a work product of this form where this I is a real interval with a metric minus dt squared. F is a Riemannian manifold, and this rho is a positive function called the warping function, so that the metric in this space is given by this expression. Or more formally, if we define sigma pi the projections of M bar over each one of the factors, then our metric is given in this form. Okay. We also recall that classical Robertson-Walker space is generalized Robertson-Walker space such that the fiber F has constant sectional curvature. And in particular, this happens if and only if M bar has also constant sectional curvature, and these curvatures are related in this way by means of the warping function. And our examples of Lorentzian manifolds, the Lorentzian space forms, may be expressed as this kind of warp products. So what happens in this case? A null hypersurface can be seen always as a graph of a function in this space, and we have this maybe well-known result that this is a null hypersurface if the function f satisfies this kind of equation. So it is called a transnormal function. In this case, we have this expression for the vector field psi, and this expression here for this vector field n. And if we calculate the shape operators, we have that they are related by this formula here in red. Okay, so now let us recall that this is a projection P. So in this case, the shape operators are linearly related if and only if our rho prime is constant, is 0. So rho must be constant. Okay. In some other cases, when we don't have this linear dependence between the shape operators. So it is natural to extend the definition of Attendant and Dugal by giving this definition. We say that a null hypersurface is locally screen quasi-conformal if the shape operators are related in this way, like in the previous example. So we have a local definition, a global definition, and we were able to generalize the results by Attendant and Dugal, just as an example. If a null hypersurface is quasi-conformal and screen quasi-conformal, then the screen distribution is integrable, and M is totally umbilical if and only if each leaf of the screen distribution is also totally umbilical as a codimension 2 submanifold of M bar. As another example, let us define the following concept. We say that the shape operator here is screen parallel if this derivative is 0, okay? And well, this can be seen also that in the sense that Nabel star and the operator, the shape operator Xi star commute in this way, okay? And in particular, this will imply that the tensor, the curvature tensor of the screen distribution and this shape operator commute in this way here. Okay. So now let us illustrate what happens in the classical case of Robertson-Walker, and in this case, The shape operator is a screen parallel in the sense above, if and only if the shape operator of each leaf is parallel. Okay. So we have also an exact relation between between these two concepts. Mm-hmm. Well, let's see what happens in this case with this principal curvatures. Let us recall the definition. We know that the shape operator here is we can diagonalize it, no? And it also has a zero eigenvector. So we have a frame field of eigenvectors of this shape operator, and such that these ones are form an orthonormal frame field. Okay. As usual, these numbers are called the screen principal curvatures of our null hypersurface. Okay. So we have a nice relation between these screen principal curvatures, which is given in this lemma here. It's just a calculation, but it can be used in the following way. Okay. Let us give this particular case. Consider a null hypersurface of a Lorentzian manifold with constant curvature and screen parallel shape operator. Okay. Also suppose that our null hypersurface is a screen quasi-conformal. So we have this relation here for these screen principal curvatures. Okay. So what happens in this case? Mm-hmm. If there is an index such that this expression is different from 0, mm-hmm, then our shape operator has at most two different non-zero screen principal curvatures, because this expression is 0 when this is 0, or this one is 0. But in this case, we may give this lambda in terms of the other. Namely, we have this expression for our our other screen principal curvature. So, and somehow we know what happens when we have two principal curvatures. So now we can give more details here. Just remember our hypothesis. M bar has constant curvature, and the null hypersurface has screen parallel shape operator, is screen quasi-conformal, and has exactly two screen principal curvatures different from 0 at each point. With this hypothesis, we define these distributions here. The distribution corresponding to each eigenvalue. Mm-hmm. And they have nice properties. They are, in fact, differentiable, and also they are involutive. So it means that we will have a structured theorem for these null hypersurfaces. Mm-hmm. Well, here is one interesting lemma with all these hypotheses, and also if the dimension of these distributions is greater than 1, then we have this property here, or this property here, which means that our screen principal curvature is constant along the leaf of T lambda or T mu. If, moreover, this null hypersurface is screen conformal, okay, then we also have that the other screen principal curvature is constant along the leaf of T lambda, okay, and the same for the other screen principal curvature. So we have this nice property. Just recall that null hypersurface is null screen isoparametric if the screen principal curvatures are constant along each leaf of the screen distribution. Okay, so our lemma before we restated in this sense. With this hypothesis, we have that the null hypersurface is in fact null screen isoparametric. And so we have this kind of result. With this hypothesis, a null hypersurface screen conformal with a screen parallel shape operator and two different non-zero screen principal curvatures with this condition on the main dimensions of these distributions, then M is locally a product of this form, where C is a null curvature, is an integral curvature of our vector field xi, and mu lambda, M lambda, and mu are leaves of these distributions. And as they are also like and M lambda and M mu are also totally geodesic in the screen distribution with curvatures given by this formula here. So this kind of null hypersurface with screen parallel shape operator have a nice structured, nice geometric structure. Okay. So, well, let's take some more minutes to give some to talk about the work in progress with Matthias and Didier. We are studying this kind of problem. If we have a null manifold and a Lorentzian manifold, M bar, when it is possible to give an isometric immersion of M into M bar. Let us give some precise statements in the following way. Okay. Let us first suppose that M bar is a Lorentzian manifold and M is some manifold here, some differentiable manifold, and give F an immersion. Okay. So as it is well known, we may induce a metric on M in this way. And we say that in this case, F is an isometric immersion. So we will consider the case where G is a degenerate metric. Okay. So as before, we may define all these objects, the radical distribution, which satisfies these kind of things. All sections of the radical bundle are orthogonal in this way to the to every other vector field on M. We fix also some screen distribution, which satisfies this kind of direct sum decomposition, and we also have over M this bundle here with fiber the tangent bundle of M bar, and given the screen distribution, we also have one-dimensional distribution, which is called the transversal distribution, which satisfies this kind of things. Okay, so we just express here our conditions on the geometry of the tangent bundle and the transversal bundle. So we also have these Gauss-Weingarten equations as before, but let me say some things about the curvature tensors. We have these lots of curvature tensors because we have now 5 connections related, and we have this kind of Gauss-Cardassian equations. In this case, where we have this is the curvature tensor of the ambient space. This one is the curvature tensor of M, etc. Okay, so we have this this kind of equations, and we also have the Ricci equations in this form. Okay. So this happens when we have an immersion of M into M bar. So how can we express this isometric immersion problem, which is of course an abstract problem? We do that in the following way. We give a null-dimensional manifold, a screen distribution, a radical distribution, which satisfies also these kind of things. We give a torsion-free connection. It is not a metric connection on M, but restricted to the screen distribution. It is a metric connection relative to the metric G. We also have these Gauss-Weingarten equations, which are well defined. Okay, and for the abstract problem, we give one-dimensional vector field E, which will play the role of the transversal bundle. Okay. Then we want to obtain this kind of theorem. We have we almost finished this theorem. We have some details pending, but it is a nice theorem. We have a null manifold simply connected with all these elements and screen distribution, one-dimensional vector field over M. We define this this vector field as the sum of Tm and our vector field E. We give a metric and a connection on this vector bundle, which satisfies some nice properties in order to have this compatibility between metric and the connection. And also we have we imposed the conditions that the Gauss-Codazzi-Ricci equations hold on this bundle for the case of R bar equal to 0. Then we have an isometric immersion of this null manifold into the Lorentz-Minkowski space. And we have a vector field, a vector bundle isometry between this abstract bundle E and the transversal bundle of the immersion of F in the Lorentzian-Minkowski space, such that the second fundamental form of H of the immersion is related with the second fundamental form on E, and we have also this relation between the transversal connection and the connection we give on our abstract vector field E. So we have this notion of isometric immersion, and we also have some kind of uniqueness if we have some two isometric immersions of the null manifold, which are some kind of related in this way. Then the immersions are related by linear isometry between in this space, satisfying this kind of relation. So this theorem, as said before, is for the case of zero constant curvature. We will try to extend this theorem in the future for all other cases of constant sectional curvature. Well, that's all I want to say. Here are some references. We have some books here. A nice book by Marcus Daxer and Rui Tojeiro. And also we have this, this book on null submanifolds. As said before, this some results were obtained by Matias Navarro, Didier Solis, and me in these papers, and some of them were obtained by myself in this last paper. So thank you very much. Muchas gracias.